Hello InventX viewers and participants. I'm Palaswamy Chakalingam. Today I'm going to present on the research topic a comparative study of vortex behavior and thrust force for innovative toroidal propeller design. This research work is done by Yahya and myself. So we are from Faculty of Engineering and Technology, Multimedia University, Malacca. In this presentation, my presentation follows like this. Introduction. Propellers have been fundamental in various fields including aviation, marine transportation and drone applications. Comes in several shapes and design. Propellers main parts are blades, hub and hub housing for shaft. Mechanism of propulsion is blade rotational movement pushes against the fluid, creating thrust force that moves the vehicle forward or upward depending on the application. Toroidal propellers represent innovative approach for propulsion system characterized by the unique ring-shaped configuration. Objective of this research work is to develop a model conventional and toroidal propeller design consists of 2 and 3 blades using SolidWorks to analyze the thrust generation and vortices formed using ANSYS fluid simulation. Compare the efficiency of a toroidal propeller with the conventional propeller design. Problem statements. Limited battery life, noise produced, control and stability, early stage wing damages. Literature review, thrust force generated due to the pressure difference that is formed between the upstream and the downstream of the blade shown in the figure 5. What is this swelling of fluid around the central axis occurring in both liquid and gases. This swelling arises from the differences in the fluid spread or density as shown in the figure. Attack angle between the chord line and the direction of fluid velocity shown in figure 7. SolidWorks is used, ANSYS Fluent is used. Methodology used in this research work is a selection of the number of blades and designing in the software and analyzing in the ANSYS, and then comparing the result and finding the result. 2 and 3 bladed conventional and toroidal propellers are designed and their results are analyzed. Case 1, twin bladed conventional propeller design with a 30-degree attack angle at 6000 rpm. Very small streamlined flow is observed through the system, and vortex profiles, however, greater vortex turbulence regions are found to have been generated. Case 2, a tri-bladed conventional design, 30-degree attack angle at 6000 rpm. A relatively less streamlined flow is observed with a very small spread of air through the streamlines and vector images presented. High vortex turbulence formulation is observed. Maximum air velocity generated is 5.24 meter per second. Thrust force generated is 73.24 Newton at 5 seconds. And case 3, twin-bladed toroidal design with a 30-degree attack angle 6000 rpm. A perfect spread is observed with a uniform streamlined flow produced. Relatively low vortex turbulence is observed in toroidal fan designs. Maximum air velocity generated is 4.93 meter per second. Thrust force generated is 74.31 Newton at 5 seconds. Case 4, tri-bladed toroidal fan design, 30-degree attack angle at 6000 rpm. A very non-uniform but streamlined flow is witnessed from the simulation. The airflow asymmetrically through the blade, hence causing an imbalance during the flight. Vortex turbulence is low. Maximum air velocity generated is 8.05 meter per second. Thrust force generated is 447.29 Newton at 5 seconds. Case 5, twin-bladed toroidal design, 30-degree attack angle at 8000 rpm. A relatively uniform and streamlined flow is observed from the fan at a higher rpm. However, the behavior of the air flowing out of the fan exhibits sudden dip in velocity. This dip can generate imbalance and malfunction during the flight. Maximum air velocity generated is 7.04 meter per second. Thrust put generated is 88.04 Newton at 5 seconds. Comparative analysis. A comparative examination of the propeller performance identified case 4 as a standout configuration, showcasing superior thrust push generation and uniform airflow. Figure 18 illustrates the performance of each propeller design in terms of the air acceleration and velocity. Case 4 achieved the highest air velocity while the case 5 showed the sudden drop. Figure highlight the downward thrust force over the time with the case 4 is excellent. A comparative analysis displaying the wind spread variation, emphasizing the efficiency of the propellers with the uniform wind speed spread in improving the thrust generation and stability. Conclusion, wind-bladed toroidal design performs the best in terms of producing the downward thrust and streamlined airflow. 6000 RPM is ideal for the propeller used in the drones at a higher RPM. In case of case 5 causes the greater turbulence. These are references used in this. Thank you. If you have any question, you can contact using the email displayed.